using probability and kind of understanding how to solve a word problem, using a contingency table. I'm not actually going to use Bayes' theorem here because I think it's a little simpler when you fill out the contingency table and just kind of look at the columns and rows. Um, but basically, I'm using an example here about a real world example. Actually, this was done in a scientific study, and it's particularly germane because in the last year or so there have been some studies contesting whether it's actually worthwhile to get mammograms to test for breast cancer, because apparently the results can be misleading enough that it it's often worse off for you to get tests under certain circumstances. Not that you should be taking advice from me, but there was a lot of research and a bit of press coverage of this in the last year or so. But basically, also I wanted to point out that most of my sample problem here is taken from it's taken from an essay by somebody whose name I'm not going to attempt to pronounce. Um, but it's basically, this is an essay that attempts to explain Bayes' theorem in a relatively simple and easy to understand way, and I think it does a pretty good job. So if you want to read up on it, I'm going to provide the link at the end here. But here's our story. 1% of women at age 40 who participate in routine screening have breast cancer. And out of that 80%, or and that out of that, so 1% of the women actually have breast cancer. 80% of the women who have breast cancer will actually get positive results on their test, and 9.6 of the women who don't have breast cancer will still get positive results. So we're going to work through this problem, and I'm actually going to use a spreadsheet this time instead of trying to write it out. So let's just take a look at the first sentence here. So how are we going to construct? We want to actually build our contingency table here, using the information that's given to us in this word problem. So I'm going to bring over a spreadsheet into my little video recording space here. So our first piece of information is that 1% of the women really do have breast cancer. So let's go ahead and set up our contingency table. Let's say here's our people who have cancer. Actually, let's do it this way. Test positive, have test negative, and then there's ones that have cancer, and then we don't actually have cancer. All right. So you can see how between, in these four spaces, we're going to have every possible combination of people who take the breast cancer mammography test. There's going to be the people who don't have cancer and yet test positive, and that's going to be in this cell. There's the people who test positive and do have cancer. Then there's the ones who test negative but still have cancer, the false negatives, and then there's going to be those who actually don't have cancer. And if you remember the terms we used in class, so here's our true positive, and then here's our false negative, and then here's our false positive, and then our false negative. Or wait, no, true negative. All right. So how are we going to figure these out? Well, I find that the easiest way is we're told 1%. I think the easiest way to figure this out is to make up a number of, rather than trying to deal with percentages and probabilities, we're going to kind of think in terms of actual numbers. So let's say that 1 million women receive the mammography test. Oh, come on, let's delete this stuff now. So that's our total, like that's the total number of people who take the test. And what we're being given right here is that out of that 1 million, 1% actually have cancer. So we can put that number in right now. What's 1% of a million? It's 10,000. All right, so that's our number who actually have cancer, and we know that if 10,000 have cancer, then that must mean that there are 990,000 that do not have cancer. So just from this little bit of information here, we were able to fill in our marginal probabilities or marginal frequencies that tell us 1 million women were tested. And again, remember, I just made this up. I could have made this 1,000, or I could have made it 100 million, or I could have made it 10. It doesn't really matter, but I picked a nice big number because it's going to prevent us from having to deal with um, a lot of decimal places and stuff. We can just do everything with whole numbers, and I think that makes it a little bit easier. But again, this is arbitrary. It could have been whatever. So then, what's our next little bit of information? Well, that's that 80% of women who have breast cancer will get positive mammographies. So that means if we have cancer out of our 10,000, so it says, out of those who have cancer, 80% of them will get a positive test result. So we know we're working with those who have cancer, which means we know we're working with 10,000. So that means 80% of the 10,000. So 80% of the 10,000, those are the 10,000 that actually have cancer. 8 out of 10 of them will receive a positive result. So that's going to be 8,000 women will get a true positive result. They have cancer, and the test confirms that they have cancer, and the test is actually right. And that means out of the 10,000, if 8,000 get a correct positive, we know that 2,000, unfortunately, will be given a false negative. They have cancer, but the test did not detect it, um, which is kind of a bummer if it turns out that you're one of those 2,000. Um, so now we filled out a little bit more of our information here. 80% of the women with breast cancer will get positive mammographies. So the question now is, can we fill out anything else? Not really. We're gonna have to look at the next little sentence that we're given of information here. So let's do that. There's 9.6% of women who do not have breast cancer. So now we're looking at out of this 990,000, 9.6% of them will also get positive mammographies. So those are our false positives. You don't have cancer, but you're still being told that you do. So what's 9.6% of 990,000? Well, that's more than I can do in my head. So I'm going to go ahead and pull up a calculator here. And we'll say 0.096, that's 9.6% times 990,000 equals 95,040. Yes, that's the right answer. So we have 95,040 women who do not have cancer are being told by the mammography that they do have cancer. Um, Also, kind of a problem if you're a proponent of screening. That's a lot of people slipping through and getting a false result. And that means that this last one right here we know is going to be this number minus this number. So let's pull the calculator in again. That's 990,000 minus 95040 is that number. 894,960. Oops. 894,960. Okay, so we just made up that 1 million number. We completed this contingency table to tell us, if we were to hypothetically test a million people, this is the numbers that we would expect to get, in the accuracy of our mammogram test. I'm going to go ahead and calculate the other marginals just using the spreadsheet. So we're going to say that equals that plus that, and that one equals that plus that. And so there we go. We've completed our contingency table. Um, just so remember, a contingency table shows us joint events, the probability that any particular random person will be have cancer and get a positive test, the probability that, or the frequency, I should say, of any particular random person getting a positive test but not having cancer, the frequency of someone who has cancer getting a false negative, and the frequency, the vast majority, fortunately, is the people who do not have cancer and also get a test result that affirms that they do not have cancer. So let's go ahead. I may have to shrink this a little bit. Get out of here, calculator. And look at our final question, um, which is, whoops, a woman in this age group had a positive mammography in a routine screening. What is the probability that she actually has breast cancer? So now we're actually being asked a question that's going to involve conditional probability. And we haven't done any conditional probability yet in this problem. We've only been doing joint and marginal. So how do we do a conditional probability? Well, the easiest way, in my opinion, especially when we're dealing with frequencies, is to say, okay, well, when we're being told that she got a positive result, we're conditioning on a positive result. So we're assuming that she falls into this column right here, this B column. She received a positive test, and that means she is one of these 103,040 people. And we can basically ignore the rest of our contingency table now. We're only looking at these numbers. So the question is, again, I made this too big. Um, well, I'm not going to be able to do anything about it. There we go. So she's one of the 103,000 who got positive test results. What is the probability that she actually has cancer? And I don't know if you guys look when you first saw this question way back at the beginning. I don't know if you probably the natural assumption, and this is even what doctors, we're talking about people who have gone, for years and years to med school and are extremely well educated, still are pretty poor at actually coming up with this number. Basically, what was it? About 85% of doctors are way off when they're given this same problem. They're way off in their assumption about how likely it is that someone who gets a positive test result actually has cancer. So let's figure it out. So in order to do this, what we want to do is take, oops. Um, so the probability of her having cancer is going to be 8,000. She's one of the 8,000. What's the likelihood of her being one of the 8,000, given that she's one of the 103,000? Well, it's literally just 8,000 divided by 103,040. Let's go ahead and get our calculator back. So it's 8,000 divided by 103,040. And that's 7%, 7.7%, and that means that this is real numbers. This is actual stuff from the world of science. If you go and get a screening for breast cancer and you get a positive result, and you're a woman over the age of 40, statistically, the probability of you actually having breast cancer is still quite low. I mean, it's 7%, so less than 1 in 10 of the times, which is one of the reasons why it's been argued that this can be misleading. Now, again, I'm not a doctor or a statistician, so you shouldn't be making life decisions based on me, obviously. But um, that's kind of surprising. Most people would not think that when you get a positive result, it's like, well, now it's time to panic. Well, the reality is, when you get a positive result on a mammography, what it's time to do is to do maybe a more selective test, like a test that has a much lower uh, false positive rate. And I think that my understanding is that that's generally what happens, is you'll end up getting a biopsy or something like that. Um, but basically, that's our answer right there. Is that given that a woman has a positive result for breast cancer from a mammography, um, only 7% of the time will that woman, or well, closer to 8%, about 8% of the time, that woman will actually have breast cancer, and the other, 92% of the time, she does not have it. Surprising result, but that's one of the things that we can get out of this contingency table, or we can also do it using Bayes' theorem if we want. But still, very surprising. So I'm going to go ahead and post a link here that has go away, the link to the article or the journal, the paper that I took this from, so that you guys can read it if you're interested. But yeah, that's that.